We will start chapter 5 today on polynomial and rational functions. We are going to cover eight sections. We will start today. We will cover the first 4 sections, and then on Wednesday, we will cover the remaining 4 sections. So in this section, 5.1, quadratic functions, we are going to learn how to recognize the characteristic of a parabola, to understand how the graph of a parabola is related to its quadratic function, and to determine a quadratic function's minimum or maximum values. We learn also how to solve problems involving a quadratic function's minimum or maximum values. A quadratic function is similar to a polynomial function of order 2. The degree of a quadratic function is 2. So a polynomial of degree 2 is called a quadratic function, essentially. With a different from 0, we have ax squared plus bx plus c. Written in standard form is f of x equal to a times x minus h squared plus k. This is done by using a formula similar to a completion of the square, where h here is minus b over 2a and k is the image of f by f, which is f of minus b over 2a. So hk is called the vertex. Example, find the vertex of a quadratic function f of x equals to 2x squared minus 6x plus 7. So using the formula, we have h equals to minus b over 2a, which will be 6 over 4 equals to 3 over 2. And the image of 3 over 2 by f is 2, 3 over 2 squared minus 6, 3 over 2 plus 7, which equals 5 over 2. So if we want to rewrite the quadratic function 2x squared minus 6x plus 7 in standard form, we will write it as f of x equals to 2 times x minus 3 over 2 squared plus 5 over 2. The domain of a quadratic function is all real numbers. That is, all real numbers can be used to obtain the image from a quadratic function. So the range of a quadratic function is all the values that are either above the image of the x, the h, the point of the vertex, or below h, depending on whether the function is positive, whether a is positive or negative, that is the leading term a. So the parabola, if the parabola looks downward, the parabola looks downward when a is negative, and in that case, the range is from the maximum f of minus b over 2a, I'm sorry, from negative infinity to f of minus b over 2a. So if the parabola looks downward, the range will be from negative infinity to f of minus b over 2a. So in standard form, if f of x equal to a times x minus h squared plus k with a positive a, the value is f of x is greater than or equals to k. That is the range. The range of a quadratic function written in standard form with a negative a, that is the negative leading coefficient a, is f of x is less than or equals to a. Let's look at this example. Find the domain and the range of the quadratic function f of x equals to minus 5x squared plus 9x minus 1. Here, a equals to negative 5 is negative. So the parabola opens downward and has a maximum value at the vertex. So we need to determine the maximum value by computing the image of the vertex, which is k equals to f of minus b over 2a, and replacing it into the quadratic expression, we will get 61 over 20. So the range is all values that are less than or equals to 61 over 20. So this is a representation of two quadratic functions expressed in standard form. The first one, open upward, that is, the leading coefficient a is positive. The range is from 1 to infinity. The second one, open downward, the range is from negative infinity to 4. Those are the possible values of f. Example, a ball is thrown upward from the top of a 40-foot high building at a speed of 80 feet per second. The ball's height above ground can be modeled by the equation h of t equals to minus 16t squared plus 80t plus 40. When does the ball reach the maximum height? What is the maximum height of the ball? When does the ball hit the ground? So these are questions of application of the vertex and x-intercepts. So the ball reaches the maximum height at the vertex of the parabola h, which is minus b over 2a, and which is 5 over 2, which is 2.5. So the ball reaches a maximum height after 2.5 seconds. So that maximum height is obtained at the value k of the vertex equals to h of minus b over 2a, which is 140. So the ball reaches a maximum height of 140 feet. To find the time the ball hit the ground, we need to determine when the height is 0. So that is h of t equals to 0. It leads to the solution of the quadratic equation, which have two possible values, minus b plus or minus square root of delta over a, which is minus 80 plus or minus 89, 60 over minus 32. So the two possible values are 5.458 or t equal to minus 0.458. So the second answer is negative, so we cannot consider it as the time. So we will say that the ball will hit the ground after about 5.458 seconds. Now let's look at this example. The parabola is drawn here, and we can see the point where the ball reaches its maximum, 2.5, 140. So notice the graph does not represent the physical part of the ball upward and downwards. Keep quantities on each axis in mind while interpreting a graph. Another type of function, which is a particular example of polynomials, is called the power function. In 5.2, we are going to learn how to identify power functions, how to identify the end behavior of the power function, identify polynomial functions, and identify the degree and leading coefficients of polynomial functions. So power functions are defined as f of x equals to k times x raised to power p, where k and p are real numbers, and k is known as the coefficient. Example, f of x equals to 5x cubed is a power function, but the function f of x equals to 2 raised to power x is not a power function. It is an exponential function, which we will learn later. In your future mathematics classes. Examples of power functions are listed below. f of x equals to 1 is a power function of with p equals to 0. So f of x equals to x is the identity function. It's a power function with p equals to 1. F of x equals to x squared is the quadratic function. X cubed is the cubic function. 1 over x is the reciprocal function. And here we have f of x equals to 1 over x squared. Let me fix this. Is the reciprocal squared function. F of x equals to 1 over x squared. It's also a power function. F of x equals to square root of x is a power function. Actually, this is the same as saying x raised to the power of 1 over 2 x raised to the power 1. I will change this into 1 over 2. So it's a power function. The cube root of 3 is also a power function. We can write it as to make it actually look like the power of x. So these are examples of power functions. We can see here examples of graphs of some power functions. On the left, you have the graph of power functions when the power is an even number. And on the right, you have examples of the graph of power functions when the power is an odd number. So here we have represented some graphs with the limit at infinity. So the first one, when the powers are even and the coefficient k is positive, it is like a parabola upward. The limit at minus infinity equals to the limit at infinity, which is infinity. For odd functions, the limit at minus infinity equals to minus infinity. The limit at positive infinity equals to positive infinity. Excuse me. For negative k, we have the parabola is down. It's not really like a parabola. It's the representation of a graph with a power function with an even power. So it's a deformation of the graph of f of x equals to minus x squared. So here, when x tends to negative infinity or positive infinity, the limit is negative infinity. When k is negative, both limit when x tends to negative infinity and when x tends to negative infinity, the limit is positive infinity. And when x tends to negative to infinity, the limit is negative infinity. So we can see in the graph here for the negative, for an even power when k is negative, for an even power, you can see both limits are negative. I'm sorry, both limits are negative infinity. There is a little mistake here from the textbook. So it's minus infinity. The limit is minus infinity because even power takes both negative and positive number to positive, and the coefficient is k is negative, so it goes to negative infinity. And when k is negative, we have the reverse of what we had upwards. So when k is negative, as x tends to negative infinity, the limit is infinity, positive infinity. and as x tends to infinity, the limit, positive infinity, the limit is minus infinity. So a polynomial function is actually the sum of several power functions. So when the leading coefficient an is different from 0, the polynomial is of degree n, and each ai xi is called the term of the polynomial, and the leading term is an xn. So the term with the highest power of x is called the leading term of the polynomial. So how do we identify the n behavior of a polynomial functions? That is, as x tends to infinity, what happened to the polynomial? If an is positive and the leading term, or the degree is a positive number, n, then the limit both for negative and positive infinity will be infinity. If n is odd, the limit will for negative infinity is negative infinity, and the limit for positive infinity is positive infinity. Now, if an is negative and n is even, then the limit is infinite, negative infinity for both positive and negative infinity. And if n is odd, the limit as x tends to negative infinity is positive infinity. The limit as x tends to infinity is negative infinity. So a polynomial is a more general form of power functions. Every power function is a polynomial with a single term. Example, given the function f of x equal to minus 3x squared times x minus 1 times x plus 4, express the function as a polynomial in general form and determine the leading term, the degree, and the end behavior of the functions. What we are expected to do here is to expand these polynomials, which we will expand to have minus 3x4 minus 9x cubed plus 12x squared. So this polynomial has a leading term minus 3x4. The degree is an even number 4. The leading coefficient is minus 3, which is negative. So as x tends to negative infinity, f of x tends to negative infinity. And as x tends to infinity, f of x still tends to negative infinity, because the degree of this polynomial function is an even number. Example again, determine the intercept of the polynomial with factoring. Given the polynomial function x4 minus 4x squared minus 45, we can determine the y and x-intercept. The y-intercept occur when x equals to 0. So the y-intercept here is 0 minus 45. To find the x-intercept, we need to solve the polynomial equation. Here, we can think about this as a quadratic equation when the variable is x squared. So factoring this will give us f of x equals to x squared minus 9 times x squared plus 5. And we can identify the values when the function becomes 0 at x equals to 3, negative 3, and when x equals to plus or, well, x squared plus 5 cannot be 0, so those are the only 3 0 for the polynomial. The x-intercepts are 3, 0, and negative 3, 0. So we have two x-intercepts. Now we want to look at a graph and learn how to identify the 0 of the polynomial described by the graph. So let's look at this polynomial here. We will identify that the graph will cross the x-axis 1, 2, 3 times. So we will have 3 intercepts. These are the 0 of the polynomial. We can see that The first one is between -4 and -2. It's exactly at -3. The second one is at -1, and the third one is at 4. The y-intercept is the only point where the function crosses the y-axis, which is at about halfway between 80, -80 and -160, which is about -120. Let's try to understand the relationship between the degree of a polynomial function and the turning points. Let's look at the graph of the polynomial x4 minus x3 minus 4x squared plus 4x. The graph has 3 turning points. We can identify the turning point here. It has changed the course from decreasing to increasing, here from increasing to decreasing, and here from decreasing to increasing. So we have 3 turning points here. So given a polynomial function, we can sketch the graph following these steps. First, find the intercepts, y and x intercepts. Second, you may determine if the function is odd or even. If the function is odd or even, you may want to do just one side of the graph. The other side will be copied from the side that we have drawn. So the multiplicity of the 0 is used to determine the behavior of the polynomial at the x-intercepts. Determine the end behavior by examining the leading term and use the end behavior and the behavior at the intercept to sketch the graph. Ensure that the number of turning points does not exceed 1 less than the degree of the polynomial. That is, the polynomial of degree 2 has at most n-1 turning points. Optionally, we can use technology to check our graph. Let's look at the polynomial function f of x equal to -2 times x plus 3 squared times x minus 5. This graph has 2 intercepts at -3, which is square, that means with multiplicity 2, and at 5. The multiplicity for 5 is 1. So the y-intercept is found by evaluating f of 0, which is at 90. So the y-intercept is 0, 90. We will plot these points on our graph. So thinking about the behavior of the leading term, correct this. So the leading term of this polynomial, if this polynomial were multiplied out, will be -2x cubed. The leading term will be -2x cubed. So the end behavior is that of a vertical reflected cubic, with the output decreasing as the input approaches infinity, and the output increasing as the output approaches negative infinity. So the graph at negative infinity will be moving upward, and at negative infinity will be moving downward. This is due to the nature of the leading term, which has a negative leading coefficient and an odd power. So to sketch this, we consider that as x tends to negative infinity, f of x tends to infinity. So since f of minus x is not equal to f of x, the graph does not display a symmetry with respect to the origin. So at -3, 0, the graph bounces off of the x-axis. So the function must start increasing at 0, 90. The graph crosses the y-axis at the y-intercept, which is at 0, 90. So we have the x-intercepts here, the y-intercept. Somewhere after the point, the graph must turn back upward and start decreasing toward the horizontal axis because the graph passes through the next intercept, which is 5, 0. So this idea will help us to reflect and to understand the behavior of the graph. So we expect a graph of this shape, which is what a graphing device can provide us with. The intermediate value theorem is a theorem that can help us also to identify x-intercepts. So the intermediate value theorem states that if f of a and f of b have opposite sign, then there must be a point between a and b where the function is 0. That is, there is an x-intercept between a and b. This is an example. We have here that f of 0 is 1, and we have here that f of 2 is -3. So there must be a point where the graph is going to cross the x-axis between 0 and 2. We can also look at between 2 and 3. F of a is negative, f of 2 is negative, f of 3 is positive. So there is a point between 2 and 3 where the function will pass through the x-axis. That's the intermediate value theorem. We may not know exactly what that point is, but we know there is an x-intercept between 2 and 3. So consider the polynomial here, f of x equal to x cubed minus 5x squared plus 3x plus 6. And we identify some of the points 1, 2, 3, 4 with their images. So we can observe that 1, 0 occur at x equals to 2. And at least 2 real 0 are between 1 and 4. The first one is between 2 and f of 3, because at 1 we have 5, and at 3 we have -5. So between 1 and 3 there is a 0, which are called to be at 2. Also between 3 and 4, f of 3 is -3 and f of 4 is 2. So the signs are opposite. Between 3 and 4 there must be another 0 of the function. This is due to the intermediate value theorem. So the graph here is obtained from a graphing device, and we can identify what we are talking about. So between 1 and 3, we have a 0 at 2. And between 3 and 4, we have a 0 at the point which is kind of close to the 4, but not really at 4. Let's consider a polynomial which is factored. F of x equal to a times x minus x1 p1 times x minus x2 p2, and so on, where each power pi on each factor can be determined by the behavior of the graph at the corresponding intercept. And the stretch factor a can be determined by giving a value of the function other than the x-intercept. So how do we graph a polynomial function using when it is expressed as a product of monomials? So we want to identify the x-intercept of the graph to find the factors of the polynomial. Examine the behavior of the graph at the x-intercept to determine the multiplicity at each of those x-intercepts. And find the polynomial of least degree containing all the factors found in the previous step. Use any other point on the graph, the y-intercept may be easiest, to determine the stretch factor, that's to determine a. We'll consider this polynomial and write the formula for the polynomials. So we will first start by looking at the x-intercept. We have 3, 2, and 5. Those are the intercepts. So we are going to look at the behavior of the function at those intercepts to determine the multiplicity of those zero. So this graph has three intercepts, -3, 2, and 5. If we look at the intercept at -3, so the y-intercept is located at the point 0, -2. So at 3 equals to -3 and at x equals to 5, the graph passes through the x-axis linearly. Let's get back to the graph. We can see that at -3, the graph is kind of like a line. And at 3 also, the graph is like a line. This tells us that the multiplicity of the function at this point are odd numbers. The behavior of the graph at 2 is kind of like a parabola at 2. So the multiplicity here should be an even number. So we are going to use those information to guess how to make our so at x equals to 2, the graph bounds at the intercept, suggesting the corresponding factor of the polynomial will be of second degree. So we will think about the possible multiplicities of each of the graph. So to determine the multiplicities, we are going to think about the graph as the graph of a function which at 3 has multiplicity 1, at 2 has multiplicity 2, and at 5 has multiplicity 1. So now using that, we want to determine what a is by taking the y-intercept, which is when x equals to 0, the value should be -2, and solve for a to get a equals to 1/30. So the function should be f of x equals to 1/30 times x plus 3 times x minus 2 squared times x minus 5. So local minimum and local maximum. A local maximum or minimum at a value x equals to a is the output of the highest or lowest point on the graph in an open interval around a. If a local function, if a function has a local maximum at a, then f of a is greater than or equal to f of x for all x in an open interval around a. And a local minimum is at a means that f of a is less than or equal to f of x for all x in an open interval around a. A global maximum or global minimum is the output of the highest or lowest point of the function. Let's look at this example. We have here local maximum at 2 and 5, and a local minimum at a point between 3 and 4. So the absolute maximum here will be the maximum at x equals to 5, which is actually 5. There is only one local minimum, so it is the absolute minimum. Using local extrema to solve applications. An open top box is to be constructed by cutting out squares from each corner of a 14 centimeter by 20 sheet of plastic, then folding up to the side. Find the size of the squares that should be cut out to maximize the volume enclosed by the box. So solution, we will start with this. We'll start this problem by drawing a picture like that in figure 7 in the book, labeling the width of the cut out square with a variable w. Notice that after a square is cut out from each end, it leaves a 14 minus 2w, 1w on both sides, rectangle for the base of the box, and the box will be w centimeter tall. This gives the volume V of W equals to 20 minus 2W times 14 minus 2W times W. So this will give us the polynomial 280w minus 68w squared plus 4w cubed. This is the graph representing the box. So having this, we want to maximize the volume and determine the W where the volume will be maximized. So we have the function here, V of W, which is a graph. Because the height of 0, since the factors are W, 20 minus 2W, and 14 minus 2W, the three zeros are 10, 7, and 0. Because a height of 0 centimeter is not reasonable, we will consider only 10 and 7. The shortest side is 14, and we are cutting off 2 square. So values W may take on, the value W may take on are greater than 0 or less than 7. This means we will restrict the domain of this function to W between 0 and 7. So from the graph, we turn our focus to only the portion of the reasonable domain and look at the local maximum there. We can estimate the maximum value to be around 340 cubic centimeter, which occur when the square are about 2.75 centimeter. From this zoom in view, we can refine our estimate for the maximum volume to about 339 cubic centimeter when the square measure approximately 2.7 centimeter on each side. It's 5.4, dividing polynomials. So we are going to learn two methods of dividing polynomial. The first one is the long division method, and the second one is the synthetic division. So the division algorithm said that given a polynomial function f of x and a non-zero polynomial d of x, where the degree of d of x is less than or equal to the degree of f of x, there exists a unique polynomial q of x such that, and a unique r of x such that f of x equals to d of x times q of x plus r of x. Q of x is the quotient and r of x is the remainder. The remainder is either 0 or has degree strictly less than d of x. If r of x is 0, then d of x divide evenly into f of x. This means that in this case, both d of x and q of x are factors of f of x. So, given a polynomial, the long division method consists of setting up the division problem, determine the first term of the coefficient by dividing the leading term of the dividend by the leading term of the divisor. So following this step, we are going to look at an example practically. So we want to divide 5x squared plus 3x minus 2 by x plus 1. So we are going to express x plus 1 here, and then we look at the leading term, 5x squared, and the leading term x here, divide 5x squared by x to get 5x. So we start by writing 5x here. Then we will multiply the dividend by 5x to have here 5x. So we will have 5x times x is 5x squared plus 5x, 5x squared plus 5x. So this will give us, subtract it from 5x squared plus 3x minus 2, we will have minus 2x minus 2. That is 3x minus 5x minus 2x minus 2 minus 0 minus 2. Now we will do the same thing. We want to divide the minus 2x here by x. It will give us minus 2. That is the minus 2 that we have here. We will now multiply this minus 2 by x plus 1 to get minus 2x minus 2. Minus 2x minus 2. Adding this up, we have 0. So x plus 1 is a factor of 5x squared plus 3x minus 2. And the result is 5x minus 2. So we can say that 5x squared plus 3x minus 2 divided by x plus 1 equals to root 5x minus 2. So x plus 1 and 5x minus 2 are factors of the quadratic expression. Let's look at another example. Here we want to divide 6x cubed plus 11x squared minus 3x plus 15. So we place it on the division graph, and we divide 6x cubed minus 3x to get 2x squared. 6x cubed divided by 3x to get 2x squared, which we multiply by 3x minus 2 to have 6x squared minus 4x squared. So we divide 6x cubed by 3x here to get 2x squared, which will be multiplied here to get 6x squared minus 4x squared. Subtract it from the original polynomial. We are going to get 15x squared minus 31x. Now we will divide 15x squared by 3x to get 5x, which make our second term here. This 5x we multiply it by 3x minus 2 to get minus 15x squared minus 10x. Subtracting from up, we have minus 21x plus 15. So the remainder here is 1. So the division here will give us 6x cubed plus 11x squared minus 31x plus 15 over 3x minus 2 is equals to 2x squared plus 5x minus 7 plus 1 over 3x minus 2. So this is the procedure for long division. Synthetic division is used when you are dividing a polynomial by a monomial, like the form x minus k. In synthetic division, we ignore the variable x and we only use the coefficients. So for example, if we want to divide 5x squared minus 3x minus 36, let me fix this. We want to divide this quantity by x minus 3. Then we will take k equals to 3. Remember, we are dividing by x minus k. Here is x minus 3. K equals to 3. So we place 3 here. And then the coefficients of the polynomial, 5 minus 3 minus 36. Then we will take the 5, the leading coefficient, we take it down to be 5, and then multiply it by 3 to place it under minus 3. So we add minus 3 to 15 to get 12. And then we multiply this 12 by 3 to have 36 and add this number to get 0. So the result is 5x plus 12. So because this remainder, the remainder is here is 0, the polynomial will divide to get 5x plus 12. So x minus 3 is a factor of the original polynomial. So let's do another example of synthetic division. Here we have minus 9x4 plus 10x cubed plus 7x squared minus 6 divided by x minus 1. Here k equals to 1, so we place k here, and the coefficients of the polynomials are up here. So we bring down the leading coefficient minus 9 and multiply it by 1 to get minus 9 here. Adding these two numbers, we get 1. Then we multiply again 1 by 1 to put 1 here. 7 plus 1 is 8. Then we multiply 8 by 1 here to get 8 here. 8 plus 0 is 8. then we multiply 8 by 1 again to get 8 here. Minus 6 plus 8 is 2. So we will use now this information to get our result. Minus 9x squared cubed. So minus 9x4 plus 10x cubed plus 7x squared minus 6 divided by x minus 1 will be equal to minus 9x cubed plus x squared plus 8x plus 8 plus 2 over x minus 1. Using polynomial division in an application. The volume of a rectangular solid is given by the polynomial 3x4 minus 3x squared minus 33x squared plus 54x. So the length is 3x, the width is x minus 2, and the height is unknown. How can we find the height? So we know that the volume of a rectangular solid is V equals to length times width times height. So we are going to use this formula to identify the height. So the height, the expression of the volume is equals to 3x times x minus 2 times h. So we are going to solve for h. So by dividing both sides by 3x, we have 3x times x minus 2 times h over 3x. So finally, we will have we divide both sides by 3x. 3x is actually a factor. We will have x minus 2 times h equals to 3x cubed minus x squared minus 11x plus 11. I'm sorry, plus 18. Now we need to divide the cubic function x cubed minus x squared minus 11x plus 18 by x minus 2. We can now use the long division here, k equals to 2. So we will write 2 here. We bring the leading coefficient 1 down, and we multiply by 2. We have 2 here. Adding this, get of 1, which we multiply by 2 to get the 2 we have here. Adding this gives us minus 9, which will multiply by 2 to have 18, and we write it there. So the remainder here is 0. So the answer to that division is minus 9 plus x squared, or x squared plus x minus 9. So that is the value of h. So we are going to stop here because I want to continue 5.5 later.